Ever wondered how computer architectures manage subroutine calls and maintain program execution flow? Well, the answer lies in a fascinating concept known as stack instructions. These are specific instructions that facilitate the use of a stack data structure in computer programming. Now you might be wondering, what exactly is a stack? It's a last-in, first-out or LIFO data structure, where elements are added or removed from the top of the stack. Stack instructions are the unsung heroes in the world of programming, playing a vital role in managing subroutine calls, handling local variables, and maintaining the flow of program execution. They are the conductors of the orchestra, if you will, ensuring every component works in perfect harmony to create a seamless user experience. So, are you ready to delve deeper into the world of stack instructions? In the next few minutes, we will do just that. Starting with the basics, let's talk about push and pop instructions. These two instructions are fundamental to the use of a stack data structure in computer programming. They allow us to manage data in a way that follows the last in, first out or LIFO principle. The push instruction is like placing a new book on top of a stack of books. It adds a value to the top of the stack. In the realm of assembly language programming, this might look like the command push X. Here, the contents of register AX are pushed or added onto the top of the stack. Now, imagine you need to use the top book on your stack. You would take it off or pop it from the stack. That's what the pop instruction does. It removes the top value from the stack and stores it in a specified register. For instance, the command pop BX pops the top value from the stack and stores it in register BX. But why do we need push and pop? Well, these instructions are essential for managing subroutine calls, local variables, and maintaining the flow of program execution. Picture a situation where you're in the middle of a complex calculation and need to perform a smaller task before you can proceed. You can push your current progress onto the stack, perform the smaller task, then pop your progress back off the stack to continue where you left off. Of course, it's important to note that the specific syntax and behavior of these instructions may vary depending on the architecture and assembly language being used. Even so, the general principles of push and pop remain the same across different programming languages. In essence, push and pop instructions give us a convenient way to temporarily store and retrieve data during program execution. They allow us to manage data in a last-in, first-out manner, which can be incredibly useful in various programming scenarios. With push and pop instructions, we can manage data in a last-in, first-out manner. Next, we take a look at call and return instructions. Dive headfirst into the call instruction. It's like a bossy finger snap that commands the program to get moving to a different subroutine. Think of it as a traffic cop directing the flow of execution to a different part of your program, a subroutine. But it's a responsible cop. Before it sends the program off, it pushes the address of the next instruction onto the stack. It's a breadcrumb trail, a way home for the program when it's done with the subroutine. An example in assembly language would be call subroutine _ label. This means we're calling the subroutine at the specified label. Now let's turn to the return instruction. This is the hero's journey home. Once the subroutine has done its job, return pops the top value from the stack and uses it as a map to find its way back to the main program. It transfers control back to where it left off, like a bookmark in your favorite novel. In assembly language, we simply write reti to return from a subroutine to the calling routine. The beauty of these instructions lies in their simplicity and their power. They manage the flow of your program, allowing it to wander off to subroutines, but always ensuring it can find its way back home. They provide a structure and order to your code, preventing it from becoming a confusing labyrinth of instructions. Imagine trying to navigate a city without street signs or landmarks. That's what programming would be like without call and return instructions. They're the street signs of your program, guiding it on its journey through the different subroutines and back again. So remember these guiding lights next time you're programming. The call instruction, pushing the address of the next instruction onto the stack and directing your program to a subroutine. And the return instruction, popping the top value from the stack and leading your program home. Call and return instructions allow us to manage subroutine calls effectively. Now, let's shift our focus to enter and leave instructions. Enter and leave are two instructions that play a crucial role in managing the stack during a procedure or subroutine. They're like the diligent stage managers in a theatre production, setting the stage and clearing it up when the act is done. First off, the enter instruction. This is the one that sets up a stack frame for a procedure. It's like a diligent assistant preparing the workspace for the procedure to work in. In assembly language, the enter instruction might look something like this: enter 40. This tells the procedure to allocate space for 4 bytes of local variables. It's like setting up a desk with 4 slots for the procedure to use. Now, once the procedure has done its work, it's time to clean up. That's where the leave instruction comes in. Leave is like the tidy coworker who cleans up the workspace once the job is done. It cleans up the stack frame, ensuring that everything is neat and tidy for the next procedure. In assembly language, the leave instruction is pretty straightforward. It's simply leave. This tells the program to clean up the stack frame before returning. It's like saying, okay, we're done here, let's pack up and go home. So in essence, enter and leave instructions work together to manage the stack during a procedure. Enter sets up the stage, preparing the stack frame for use. It allocates space for local variables, ensuring that the procedure has everything it needs. And when the procedure is done, leave steps in to clean up. It clears the stack frame, making sure everything is back in its place. Together, these 2 instructions ensure that procedures can work efficiently and effectively. They manage the workspace, allocating and deallocating space as needed. They're like the unsung heroes of the stack, working behind the scenes to make sure everything runs smoothly. With enter and leave instructions, we can manage local variables and clean up after subroutines. Lastly, we explore the push flags and pop flags instructions. These stack instructions are particularly noteworthy due to their role in preserving the state of the program. Let's dive into the push flags instructions first. They come in 3 variants: pushf, pushfd, and pushfq. What they do is quite simple yet vital. They push the flags register onto the stack. The flags register, for those who might not know, is a special register that holds the status flags that indicate the results of operations carried out by the previous instruction. For example, in assembly language programming, you might see something like pushf. This command pushes the flags register onto the stack, preserving its current state. It's like taking a snapshot of the flags register and storing it away for later use. Now let's move on to the pop flags instructions. Just like push flags, pop flags also come in 3 variants: popf, popfd, and popfq. These instructions perform the opposite operation of the push flags instructions. They pop a value from the stack into the flags register, effectively restoring the flags register to its previous state. An example in assembly language might look like popf. This command pops the top value from the stack and stores it in the flags register. It's like taking that snapshot we stored earlier and restoring it back to the flags register. So why are these instructions so important? Well, they allow us to save and restore the state of the program. They're especially useful in situations where we are about to perform an operation that might alter the state of the flags register, and we want to be able to restore it to its original state later on. In conclusion, the push flags and pop flags instructions are like the unsung heroes of the stack instructions. They may not seem as glamorous as some of the other instructions we've discussed, but they play a crucial role in preserving the state of the program, making them indispensable tools in the programmer's toolkit. Push flags and pop flags instructions help us preserve the state of the program. So, we have covered the basics of stack instructions. We've delved into the intricacies of push and pop, which add and remove values from the stack. We explored the call and return commands, which manage the running of subroutines and their return paths. We've also looked at enter and leave, the unsung heroes that set up and clean up stack frames for procedures. Lastly, we touched on push flags and pop flags, which preserve the state of your program by handling the flags register. These instructions are more than just commands. They are the backbone of managing subroutine calls, local variables, and maintaining program execution flow. They are the silent conductors, orchestrating the beautiful symphony that is your code, ensuring each note plays out in perfect harmony. In computer architectures, understanding stack instructions is fundamental to efficient programming. Thanks for joining us today.